Assalamu alaikum. Physical Geology, Chapter 13, Running Water, presented by Khalid Lamrouni. Khalid Lamrouni, PhD in Geology from Texas A&M University. And Khalid Lamrouni is a staff member at the Earth Science Department of Yunus University, Benghazi, Barga State, or Cyrenaica State. The reference used for this talk is Essentials of Geology. This is the Department of Earth Sciences at Yunus University, and this is the main entrance of Yunus University. Here's the Prince of Cyrenaica State, Idris Sanusi. And here's the flag of Cyrenaica State behind the Prince, Idris Sanusi. And this is Benghazi, the capital of Cyrenaica State, or Barga State. And this is Omar Mukhtar, the chief commander of the Sanusi army. And here's the map of Barga State. Outlines the hydrogeology or hydrological cycle, stream velocity and controlling factors, gradient, shape, size, and roughness of the channel and discharge, changes downstream, load and discharge, base level, ultimate and local, graded streams, work of streams, erosion, three things: erosion, transportation, and deposition. Stream ability, it depends on its competence and capacity. Transportation in three ways: dissolved load, suspended load, and bed load. Stream channels, bedrock channels, alluvial channels, which includes meandering and braided channels. Stream landforms, deltas, natural levee, alluvial fans, floodplains. Two types of stream valleys: narrow, V-shaped valleys and wide valleys with floodplain, floodplain. Drainage systems and patterns, and then stages of valley development, and then we'll go through incised valley and terraces, and then floods and flood controls. Here we have a lot of definitions, and we'll make sure we'll focus on the main important things. So the hydrological cycle describes the movement of water through Earth's four spheres: geosphere, hydrosphere, atmosphere, biosphere. In short, the hydrological cycle talks about precipitation from the clouds, comes down to the earth as runoffs or infiltrated down under the ground as groundwater. And then this runoff will go to the ocean or to the lakes. And then what will happen? Evaporation from the oceans and lakes and transpiration from plants. And both will create vapor, and vapor will condensate higher at the atmosphere to create clouds and then precipitation. So precipitation, runoff, evaporation, transpiration, and then precipitation again. This is the summary of the hydrological cycle: precipitation, runoff, and infiltration. Running water. The source of running water is rain and snow. Streams are supplied by runoff and underground water. Stream flowing water makes its way to the sea under the influence of gravity. So the main goal is sea or lakes, and then the main control is gravity. The ability of a stream to erode and transport material is directly related to its velocity. Controlling factors on the velocity: gradient, shape, size, and roughness of the channel. And then third one, discharge. Definition of the discharge: the discharge the discharge of a stream is the amount of water flowing past a certain point in a given unit of time. So discharge is a volume, is a load. And we know the water is loaded with sediments. And here we have this note: when discharge increases, the width or depth of the channel must increase, or the water must flow faster. Velocity increases too. So let's look at the relation between these changes down the stream. let's look at the changes. So here, let me explain this. The width parameter. Influence of a channel shape on a stream velocity. So here we have wide channel like 10 units and the depth 1 unit. Here we have another channel narrower with 5 units width and 2 units depth. The cross-sectional area 10 times 1, which is 10 square units. The parameter 1 plus 10 plus 1, which is 12. The ratio is the area over the parameter, the width parameter is 10 over 12, 0.83. Here, cross-sectional area is 10, is 5 times 2, and the width parameter is 2 plus 5 plus 2, which is 9. The ratio is 10 over 9, 1.1. This stream will be faster because the ratio is smaller. The smaller the ratio, the faster the stream. Here the longitudinal profile of a stream from the mountains down almost to the ocean, 0. So the distance from 0 to 150 kilometers, and the elevation, the height, 1, 2, 3, 4 kilometers. So as you are coming from the head of the stream to the mouth, the gradient is high at the head. As you're coming down to the mouth, it's getting gentle and gentle. So the whole profile is concave up profile. So channel changes from head to mouth. From the head to the mouth, we have 5 main elements. We said channel roughness, channel slope or gradient, discharge, channel size, and velocity. From head to mouth, from the top here to the mouth, the channel roughness decrease as you're coming from here, from the head to the mouth, decrease. The channel slope or gradient decrease as you come from head to the mouth. So higher gradient here, higher roughness here. As you're coming down to the mouth, lower gradient, lower roughness, getting smoother. The opposite, discharge will increase as you're coming from the head to the mouth, discharge will increase. Channel size will get wider channels here and narrower channels here, so wider as you go down. Velocity, flow velocity increases down. Let's go back here. A stream can maintain higher velocity near its mouth down, though it has a lower gradient than the upper stream. Because of the greater discharge at the mouth, lower, have greater discharge, larger channel, and smoother bed. Base level and graded streams. Base level controls stream flow. We have 2 types of base level. So what's base level? Base level is the lowest point to which a stream can erode its channel. Sea level is the ultimate base level, this first type. And we have temporary or local base level, includes lakes, resistant rocks, and main streams which act as base level for their tributaries. So when a stream enters a lake, its velocity quickly approaches 0, enters lake or ocean, and its ability to erode decreases. Any change in the base level will cause readjustment of a stream activity. Raising base level causes deposition. Lowering base level causes erosion. A graded stream has the correct, this definition, has the correct slope and other channel characteristics necessary to maintain just the velocity required to transport material. So graded streams just transporting material. A graded stream only transports sediments. No net erosion or deposition of sediments. Neither nor. So here we mentioned that raising base level causes deposition, lowering base level causes erosion. So if we built a dam here, this is a graded stream. If we build dam here, that means we raise it base level. What will happen here? Deposition. Rivers will start deposition. Will start depositing sediments at the upper levels of the valley. So the stream readjusted itself. On the other side, if we lower the base level, if a fault happened to this profile, this is a graded stream profile. If a fault happened like here, we'll have escarpment. This part fell down, so we lowered the base level. The stream will start eroding this top part above the escarpment until it reaches this dotted profile to reach to the equilibrium stage and to be a graded stream. So the stream will start eroding this part until it comes back to the graded stream profile. So lowering the base level will cause erosion. Work of streams. Streams can do three things, or transport their sediments in three things: erosion, transportation, and deposition. Erosion. Here we have notes. Although much of the materials carried by streams has been brought in by underground waters, overland flow and mass wasting. Okay. Streams do contribute to their load by erosion or eroding their own channels. For example, pebbles serve as cutting tools, bore circular holes into the channel floor called pothole. So, and this is the pothole. So there are a lot of pebbles, gravel here, and these working as means of erosion, cutting through the bedrock and creating holes and enlarging them until so let's go back to the transportation. Once streams acquire their load of sediment, they transport them in three ways: dissolved load in solution, suspended load, bed load. Dissolved load transported in solution, suspended load transported in suspension, which is mainly silt and clay, bed load along the bottom. So any stream here has can be divided three zones: the zone of erosion, higher elevation areas close to the head, and zone of transportation, which is the graded profile, a graded stream, no net erosion or deposition, and the zone of deposition close to the mouth of the river, where it creates deltas and deposits most of the sediments there. And these are the three ways of transportation. Sediments transported as bed loads, either rolling and sliding, and saltation. Mostly like pebble and boulders, rolling and sliding, sand and gravel, saltation, and then we have clay and salt as suspended load. Also, we have dissolved material, suspended, carried as suspended load in the river. Amount of material carried in suspension is controlled by stream velocity and settling velocity of sediments. So what's settling velocity? Is the speed at which a particle falls through a still liquid. We have definition saltation in the transportation, especially bed load. The saltation material that moves along the channel by rolling and sliding is occasionally lifted for a few seconds by swift eddies. This process is called saltation. Now here we have two important terms: competency and capacity. A stream ability to carry its load depends on two criteria. First, its competence. The competence of a stream is a measure of the maximum size of particles it's capable of transporting, the velocity determining its competence. So the maximum size the stream can transport, the maximum grain size, reflects its competence, and it's determined by its velocity. Higher velocity, higher competence. The second, the maximum load the stream can carry, we call it capacity. Capacity is related, stream capacity, to stream discharge. So the amount of load the stream can carry, the larger the amount, the larger the capacity, and this is determined by the discharge. So the greater the amount of water flowing in the stream, the greater the stream's capacity for hauling sediments. Hauling means transporting. Okay. Talk about here's settling velocity. So, for example, if we have a grain of 1 millimeter, here we have a grain size from 0.01 millimeter to 100 millimeters. And here we have velocity from 0.1, 1, 10, 100, 1000 centimeter per second. If we have a grain size of 1 millimeter, to be transported, the speed must be above like 7 or 7 centimeter per second or above. If it's below 7, that's settling velocity. The sediments cannot be transported and fall down in the river water and settle down. So the larger the grains, the larger the settling velocity. To transfer anything above the settling velocity here, above this curve, is transportation. So if the speed for this 1 millimeter, if it's 10 centimeter per second, this 1 millimeter sediment will be transported, carried in the water. But if it's 7 or less, for example, let's say 1, this particle will fall down. 1 centimeter per second velocity is not enough to move it. So look at the suspended load here. We have this river, looks muddy, dirty, due to the suspended sediments. Work of streams, now deposition. We talked about the transportation, the third thing, deposition. When the stream's velocity is reduced, its competence is also lowered. Consequently, some of the suspended particles begin to settle down. In this case, the material is called alluvium. So the deposits carried by the sediments, when they settle down and deposit, we call them alluvium. What they produce will produce deltas, will produce natural levees, will produce back swamps. Deltas. Delta has three, it's a triangular shape. When the stream meets with ocean or a big lake, the stream velocity will be almost zero, and the sediments will start falling down because the stream will lose its competency. And sediments will fall down and form triangular shape, which is called delta. And this triangular shape delta, so when it starts like one channel, the main channel, and over time this channel will start having branches due to changes in gradients, and the delta will grow. But the delta has three main beds. This is sets above it, top sets, below it, bottom sets. Bottom sets mostly clay and salt, fine grain size. As you go up to the four sets, it's coarser grain, sand, gravel, and it gets coarser at the top here, the top set. So let's go back. The main channel dividing into several smaller ones called distributaries. In natural levees, the rivers with the broad valley floors build a landform parallel to their channels. We call them lateral levees. And back swamps are areas behind the natural levees. We'll see them in later pictures or figures. Stream channels, bedrock channel and alluvial channel. Bedrock channel are cut into the underlying strata. Bedrock channels are cut into the underlying strata. So bedrock channels mainly when the river cuts through the bedrock, and that happens at the upper part of the stream, the head of the stream. Typically form in the headwater region where streams have a steep slope. Potholes, tips, and pools are common features of bedrock channels. Channel pattern is controlled by the underlying geology. Alluvial channels. Alluvial channels form in sediments previously deposited in the valley, typically associated with a floodplain. The channels can change shape as material is eroded and transported. We have included the alluvial channels, meandering channels, and braided channels. Meandering channels, streams transport suspended sediments in broad, sweeping bands called meandering. Meandering channels evolve over time. The outside of a meander, cut bank, zone of active erosion. The inside of a meander, point bar, is a zone of deposition. And over time, the meandering stream will create cutoffs and cutoffs oxbow lakes. And we have the other type we call it braided channel. A braid channel is a network of converging and diverging channels that thread among numerous islands or gravel bars. A large portion of the load is coarse material. Bank material is easily eroded and reworked. So let's look at the braided stream. Formation of cut banks and point bars. So as the stream bends, the braided stream as the braided stream bends, the high velocity zone, the outside part of the channel is the erosional. Like here, you see this house here, the stream cutting under erosional. But the inner side, where this yellow part is, this is depositional. This is point bar, and this is the cutoff bank. As bends here, the other deflection, here erosional, through the mountains, and here depositional. Why? Because the high velocity is here and the minimum velocity is high velocity, keeps cutting. When it requires low velocity, we'll start dropping the sediments. Here, natural picture. You see point bar, depositional, with the stream velocity is almost zero. And here, cutting on the opposite side. The same thing here, cutting at the outer side and deposition at the inner side. So high velocity, erosion, low velocity, deposition. Same here, high velocity, erosion, low velocity, deposition. So we're at maximum velocity. Okay. Oxbow lakes. So this sketch showing this stream has big deflection, and here we have neck. Over time, this one part will start cutting until connected. So when the two parts of the opposite sides of the channel connected, creating this part, we'll call it, the neck will become cut off, and this part will become isolated and becomes a lake. We call it Oxbow Lake. And here in nature, this is the cutoff, and this is the Oxbow Lake. These in meandering streams. Braided streams. These are braided streams, especially close to the top of the mountains. At the upper part of the stream, we'll see like diversion and then converging again. diversion coefficient. In between here, sandbars, gravel, sand size. And those can be easily eroded because they're not cemented yet. Stream valley, two types of stream valley, narrow V-shaped and wide valley with flat floors. So they have floodplains, and they have, and by the way, floodplains, they're erosional floodplains and depositional floodplains in the meandering, cutoff, and exposed. So we'll look at those two types of stream valleys. This is the narrow V-shaped valley, okay? And here the ones in the between, and this is the last stage wide valley. So here the V shape most of the time forms at the upper parts of the stream, at the head of the stream. It's characterized by cutting down in a head in V shape and has a lots of rapids, waterfalls, and the terrain is still mountainous around it. As the erosion increases, the river will start bending. That means the river will start cutting, will leave the cutting down and start cutting side to side, and widening its course until it creates wide plain. We call it floodplain. And as you see here, the floodplain is wider than the stream belt itself, and you will have exposed lakes and cutoffs. So, and this is so as you see here, narrow V-shaped and wide valley with flat floor. So we have floodplain and a meandering stream. That's in general, and that happens over time or through the course of the stream, from the head of the stream to the mouth of the stream. Drainage systems and patterns. So the land area that contributes water to the stream is known as a drainage basin. The drainage basin of one stream is separated from another by an imaginary line called a divide. So we have drainage basin, we have a divide. Divides range from a ridge separating two small gullies to continental dividers. And we have drainage patterns, four types: dendritic, rectangular, radial, trails. Let's look at the pictures to understand. So we have a divide, and water goes both sides out of the divide rails, and these rails will connect together to gullies, and these gullies will connect together to the valley. And we call them tributaries, and they meet together inside the valley and feed the valley. So here the divider. Here we have divider, then between two valleys, another divider. Or if you look at this Yellowstone River, you see splits here, one river, second, third, and they have dividers in between, dividers, till they meet together in one river. As you see here on the map, there's one basin, another upper Mississippi, Ohio. These different basins have dividers. Let's look at the drainage patterns here. We have dendritic pattern, the shape. We have rectangular, like 90 degrees, this shape here. We have radial, like star shape, radial, volcanic here. And we have trills pattern. So let's see why they're different. The drainage patterns. The most commonly encountered drainage pattern is dendritic pattern. Dendritic pattern forms when the underlying material is relatively uniform. So when the rocks in that area are uniform, you will have this dendritic pattern, like a vein shape. Rectangular pattern, which is 90 degrees. That means the pattern develops when the bedrock is crisscrossed by a series of joints and faults. So we have tectonics in this area when you have rectangular 90 degrees. Radial pattern is the pattern. This pattern is typically develops on isolated volcanic cones and domal uplifts. So we have domal shape, either uplifting shape, domal uplift, or volcanic dome. Trills pattern. A rectangular pattern in which tributary streams are nearly parallel to one another. This forms in areas underlain by alternating bands of resistant and less resistant layers or rocks. So we have either weak and strong layers and hard and soft layers in that area to get the trellis pattern. This is about the drainage patterns. Dendritic, uniform rock. Rectangular, you have faults and joints. Radial, you have domal shape or volcanic cone. Trellis, you have soft and hard layers exposed on the surface. Stages of valley development. Okay, we have youth, mature, 3 stages, and old. And we have also old rivers can rejuvenate. We call rejuvenated area, rejuvenated valleys. When the river abandoned the lateral erosion and revert to down cutting. What's the youth stage? The youthful stage is characterized by down cutting and a V-shaped valley, occasional waterfalls, rapids, steep gradient, little or no floodplains, and rather straight course without meandering, so no meandering. The V-shape, youth, usually upstream. So this is the youth. You have straight course, you have waterfalls, cutting down, and a head. Maturity, second stage. Once a stream has sufficiently lowered its gradient, it begins to erode laterally, producing wide valley, the gradient much lower, the profile is much smooth, floodplain, great floodplains, meandering stream, cutoffs, Oxbow Lake, and low natural levees. And then if it goes to old stage after the valley has been cut several times wider than the width of the meandering belt, it has entered the old age stage. Large flooding plain, meander, old cutoffs, Oxbow lakes, natural levees, back swamps, stream shifts more rapidly, lateral erosion. So note this, cut several times wider than the stream, cut several times wider than the width of the meandering belt. Here we go. So here we have meandering stream, and here we have meandering stream. But this is still youth, because the width of the stream belt almost the same width of the floodplain. But here we have wider floodplain, and the width of the floodplain from here to here, but the width of the stream, the belt, the meandering stream, less than the floodplain. And you have a lot of exposed lakes in this. And the stream at this stage, the youth stage, cutting down and ahead. But when it comes to youth and old, you start cutting side to side, side to side. The difference between mature and old, mature still fitting the floodplain, but the old is way, way smaller in width than the floodplain. Floodplain is way wider and you have a lot of exposed lakes. Cycle of landscape evolution. Oh, did you mention the rejuvenation? Okay. No. So cycle of landscape evolution. Downcut, erode, and eroded headward. This is youth stage. Landscape retains its flat surface, narrow stream valleys. It has narrow stream valleys. Downcutting continues. Hills and valleys. You'll have a lot of hills and valleys. And you will have lateral, and this will take you to the mature stage. And eventually streams will approach base level. Downcutting will give way to lateral erosion. And that's when you create meandering stream. As the cycle nears the old Asia stage, the effects of overland flow and mass wasting coupled with lateral erosion by streams will reduce the land to a peneplain, near plain. Once a peneplain has formed, uplifting starts the cycle again. Most often, uplifting interrupts the cycle before it reaches the old Asia stage. It's another interesting subject: incised meanders and stream terraces. Incised meanders are meanders flowing through steep, narrow bedrock valleys. We said meanders supposed to flow through wide valleys with floodplain, but if you find meandering streams flowing through wide, steep, narrow bedrock valleys, there's something wrong. That means meander first developed in a floodplain, base level drops, causing the meanders to start downcutting. Once the river has adjusted to the new base level, it will produce a new floodplain below the old one. The flat remnants of the old floodplain are called terraces. So here we have meandering river cutting down, which is very strange, supposed to cut laterally, side to side, but this one cutting down. So that means the base level has changed. If we look at this here, the explanation, this is a real picture and this is the explanation. So we have wide floodplain, we have meandering river, and then all of a sudden the base level dropped. The river instead of will give up eroding side to side and start eroding down. So when the river starts eroding down, what will happen? The old floodplain will be cut down. This is the old one, and create a new zone. As the base level dropping down more and more, another level, the meander or meandering stream will keep cutting down more and creating another level. So this is the old floodplain, and this is the newer, and this is the newest. So when you see these levels, we call them terraces. Terrace 1, terrace 2. You will know that this river, this meandering river, is not acting normal. Something happened to the base level, so the river gave up lateral erosion, side-to-side erosion, and started cutting down. So if you look at this, we'll have cliff, flat, cliff, flat. So this cliff and erosional level from here to down, and this is the terraces, the old floodplain. And there's another cliff and then a flat. This is older floodplain. And you find a cliff, flat, another floodplain. So this river had, or this meandering river had been through many cycles of base level dropping and cutting to create these terraces, levels of terraces. It's in Wyoming. Depositional landforms, deltas, alluvial fans, natural levees. Deltas form when sediment-filled streams enter a large body of water. The main channel divides into several smaller channels in the delta called distributaries. Alluvial fans, definition. Alluvial fans are fan-shaped deposits of sediments at the base of a mountain front. So we have fans in the ocean or in the lake and fans on land. The stream emerges onto a flat lowland, the gradient drops, and the sediment is deposited. Natural levees. Natural levees are raised areas adjacent to the channel formed during flood events. So if we look at the growth of Mississippi River, you'll find this Mississippi River had been through many stages. So the first delta was built here, and then the distributary diverted to this side, getting the second delta, and then third, fourth, fifth, sixth, and now seventh. And if you look at this seventh, this enlargement of the seventh delta, it has many distributaries. So as the gradient changes, the river will change its course and give you a new distributary. This is the alluvial fan. When the sediments coming from the mountains and the deposit at flat, leveled surface on land. Formation of natural levees. We have floodplain here, floodplain here, and we have river. If we came close to this river, cross section along this river here, and along the sides of the river, when the flooding is happening, what happens? Sediments will deposit over the sides. The coarser close to the channel, and the finer will be back here as you go away from the channel. This is the first stage. After the flooding, the river water will come back again here, and then next flooding happened, another level will be deposit of sediments. Over time, we'll get sediments over layers of sediments above layers of sediments, and that will create levees, flanks here. Behind the levees here, you'll find swamps. So if you look here, you'll find back swamps behind the levees. Floods and flood controls. Types of floods: regional floods, flash floods, ice jam floods, and dam failure floods. What's regional floods? Seasonal floods that typically result from spring rains or rapid melting of snow. Flash floods occur with little or to no warning in mountainous area. Ice jammed floods, ice forms in rivers, creating dams. So ice will create dams in the rivers. That will break when temperature rise. When temperature rise, the ice melts and then will flow and create floods. Dam failure floods. Dams fail and release large amounts of water. And this is the Great Flood in 1993. Here we have Mississippi River, and we have this one here, and we have Missouri River. This is before the flood. After the flood, could you see the thickness of the river channel filled with water? This is Mississippi River, and this is Missouri River. And here, flash floods in Vermont. destroying roads. And floods and flood control. Flood control, they built artificial levees, channelization, flood control dams, non-structural approach. So artificial levees, they create earth mounds built on river banks to increase the capacity of the channel, often fail in floods. Channelization, altering a stream channel to make flow more efficient, increases erosion. Flood control dams, built to store flood water and release it slowly. Non-structural approach, best approach to flood control is to limit development within the floodplains. So the take-home message that we studied here, the the hydrological cycle, stream velocity and controlling factors, which is gradient, and the channel shape, size, roughness, and discharge. And also we studied the changes downstream, load and discharge. Base level, we found out ultimate and local. And grade streams and work of streams, which is three things: erosion, transportation, and deposition. A stream ability to carry its load depends on two criteria: stream competency and stream capacity. And we talked about transportation three ways: dissolved load, suspended load, and bed load, the stream transportation. And stream channels, we find out there's bedrock channels and alluvial channels that include meandering and braid streams. And stream landforms, deltas, natural levees, alluvial fans, floodplains. And there are two types of stream valleys: narrow valley shape, V-shaped valleys, which is in the mountains most of the time, upstream stream head, and wide valley with flat floors close to the stream mouth. And we looked at the floods and flood controls. And by this, we get to the 3 minutes national anthem of Sri Lanka state. Thank you very much.